This video is on the objective, write a Cartesian equation in polar form. Okay, so this is where we're given equations with x's and y's, right, in Cartesian equation with rectangular in terms of rectangular coordinates, and asked to write an equation for the same curve, right, that will have the same exact graph, but describing the points with r and theta, right, those polar coordinates. And yeah, let's take a look. Right, so again, if you want to see more about the topic, click on More Instruction, look at their notes, their videos, their examples, and hopefully those help. In fact, I'm going to show you just a little bit of their instruction here on transforming equations between polar and rectangular forms. Converting equations between polar and rectangular forms can be a bit difficult, but it is highly beneficial to be able to convert between the two forms. Since there are a number of polar equations that cannot be expressed clearly in Cartesian form, and vice versa, we can use the same procedures we use to convert points between the coordinate systems. So hopefully you recall in previous videos talked about converting between points that are in polar coordinates, converting to rectangular coordinates, and vice versa, taking points in rectangular coordinates and converting them to polar coordinates. So all those relationships are going to come up here. So look at their example. So you write the Cartesian equation. You see it's an x and y. X squared plus y squared equals 9. Well, a quick way to do this would be remember that relationship that x squared plus y squared was equal to r squared in polar. So you have r squared equals 9, meaning that r could be positive 3 or r equals negative 3. Now they go the kind of the roundabout way here, where you remember also that x was equal to r cosine theta, y was equal to r sine theta, and then they square these and pull the r squared out and use the Pythagorean identity. Remember, cosine squared plus sine squared is 1, and then again you're seeing that r squared equals 9, or r equals 3, or r equals negative 3. And these graphs, the graph of x squared, all the points where x squared plus y squared equals 9 in rectangular, should be the same graph as the graph of r equals 3, right? This is all the points where r is equal to 3 in polar. And they're both circles with a radius of 3, right? Every point that's 3 units away from the origin would be on the graph of r equals 3. Same thing for every point that's 3 units away from the origin would be on the graph of x squared plus y squared equals 9. So they're showing you that they are indeed the same curve. Right? Okay. And that's what we're asked to do. Right? We're to take an equation right now that has x's and y's, write an equation that has just r's and thetas that would have the same graph. Right? That would draw out the same exact curve. Alright, so they give you another example here, which I will let you read through, and another one down here, which I'll let you read through. Again, if you're going through more instruction, you're going to see this stuff. Alright, so let's look at our problem. So look, we're given here, convert the given Cartesian equation into a polar equation. X squared plus y squared equals 2 times x plus 3 times y. Alright, so I'll write this out on some paper. So we have this equation. X squared plus y squared equals 2 times x plus 3 times y. Now this is in rectangular. Now I'm going to tell you right now, this is a circle. Hopefully you remember that. Alright, let me show you before I even change to polar. Let me show you that this is a circle. Remember the standard form for the equation of a circle? Hopefully you remember back to like a pre-calc 1 or some previous algebra course you've taken. Remember, it was the quantity x minus h squared plus the quantity y minus k squared equals r squared. Remember, this was the standard form for the equation of a circle whose center was the point, h comma k, and whose radius was r. Hopefully this rings a bell. So watch this, right? If I take everything to one side, x squared minus 2x, and you have plus, and then I'm leaving some space here because I'm going to be completing the square. Hopefully that rings a bell too. Then we have plus y squared minus 3y. All right, and then I have equals 0 on the other side. And then I'm going to complete the square. So remember, you need a 1 on the coefficient of the square term, and then I'm going to take half of this and square it, half the linear coefficient and square it. Well, negative 1 squared is positive 1, so I'm going to add 1 to both sides. It's still an equation. Then half of this is negative 3 halves. Squared would be positive 9 fourths. And so I add 9 fourths to both sides. Then over here we have the quantity x minus 1 squared plus, here we have the quantity y minus 3 halves squared equals, and then over here this is positive 13 fourths, right? 4 fourths plus 9 fourths. And this is the equation of a circle whose center is at the point 1 and then 1.5, 3 halves. So here's 1, 2, and then 3 halves right here. There's the center. And then the radius is the square root of 13 fourths, which is the square root of 13 cut in half, right, divided by 2. So the radius of this circle is between 3 halves and 2, because the square root of 13 is between 3 and 4. So this is between, this divided by 2, it'll be between 1.5 and 2. So between, there's 1.5 units and 2, so there's a point down here. So something like this, right? Something like this, a circle with a radius. I'm not drawing perfect pictures here, but we're going to picture like this. Its center is in the first quadrant, and the radius is the square root of 13 over 2. And I'll show you a much better picture on a website. I may have shown you this before, I don't recall. But anyway, you go to desmos.com, desmos.com. It's a free online graphing calculator. And I've got my my view here, so everything's bold. And you can start entering equations as they look, right? The equation we had here was x squared plus y squared was equal to 2x plus 3y. And you see that circle, right? And remember, I said the center was at the point, and you can just put in random points. The center was at the point 1, comma 1.5. And can you see how that green point there is definitely in the center of that circle? It looks, and even if you don't believe it, it looks pretty close, doesn't it? So there's the graph of our rectangular equation, right? Now, what we're asked to do, right, is change this so I get the same graph but described in polar coordinates. So we have to remember the following relationships, right? Here are all the relationships. I'll cover this up for now. So remember all the relationships between x and y and r and theta. We had x squared plus y squared equal to r squared, right? And these were all the same relationships you saw when you were converting between coordinates. We had x was equal to r times the cosine of theta. We had y is equal to r times the sine of theta. And we had the tangent of theta had to be equal to y divided by x. All right. So this is all we're working with, really. These were the only formulas you used to change from polar coordinates to rectangular and rectangular to polar. Hopefully these look familiar. So looking at my equation here, look at the left side. X squared plus y squared. Well, I see that. I'm going to just change that to r squared. And then 2 times x, that's 2 times r cosine theta, plus 3 times y is 3 times r sine theta. And we're really not going to focus on too much. Notice that every single one of these terms has an r in it. R squared, r to the first, r to the first. Now, r equals 0. Now, r equals 0. That's just the origin. Right? Remember when you think about the two axes, and remember the horizontal axis is the polar axis. R equals 0 means I'm 0 units away from the origin. Right? It's this point here. So that would be like one solution to this equation, r equals 0, but that's not an interesting graph. Right? That's not an interesting graph. And it's definitely not the graph of our circle. Right? Definitely not the graph of our circle. So r equals 0 would work since every term is a factor of r. So like in order to, let's ignore this and get rid of the r. Divide by r. Right? So I can divide through by r. And now we don't have to worry about this graph showing up, and then we get r equals 2 cosine theta plus 3 sine theta. All right, and here's our, and then for the most part, you're going to be asked to solve for r, like I have here. R equals some function of theta. And let me go to my Desmos website again and show you that this equation in polar gives me the same exact curve, the same graph as this equation did in rectangular. All right. So back here on the Desmos website, now if you type with x's and y's, it automatically assumes you're working rectangular. And if you type with r's and thetas, it'll assume you're working in polar, and graph in polar. So watch this. R equals 2 times the cosine of, now if you want to type in theta, you do like a backslash or you do a slash and then theta. Oh, actually you can just type in theta, no slash. All right, so theta, and it becomes theta. And then plus 3 sine of, and then spell out the word theta. Right, look at that. You see that graph? Now I'm going to have theta, usually we want theta to range from 0 to 2 pi. Right, so I'll have theta range from 0 to 2 pi. You saw earlier, even when theta ranged from 0 to pi, the graph was the same. Look, I'll turn it off. There's the graph in rectangular. The x squared, red graph is in x squared plus y squared equals 2x plus 3y. Here's the graph in polar, right on top of it. It's the exact same curve. Right. Okay. So this is what we're going to choose, right? R equals 2 cosine theta plus 3 sine theta back in the problem. So 2 cosine theta plus 3 sine theta gives me the same exact graph as this does in rectangular. Okay. And they go through it. Now again, they do it the long way where they put in, just remember that cosine squared plus sine squared equals 1. And they get the same thing. Right. See, a common factor of r can be canceled. Alright, so again, these can be tricky, right, as they said in the instruction, in the notes, right, because some equations in rectangular are very difficult to change to polar in a convenient way, and vice versa. Some equations in polar are very difficult to transform to rectangular in a nice, convenient way. But I'm hoping that most of these exercises, I'm hoping that they give you equations that'll be, reasonably simple. This one wasn't terrible, right? All right. So hopefully watching me do this, looking at the more instruction when you need to, or reading the answer explanations when they come up. And I'm hoping that all this stuff helps you when you go about working on this material on your own. And thank you for watching.